Hi, my name's John David Dalton. I'll get into a little bit more about what I do in a second. This talk is called Unorthodox Performance, and it is about the performance optimizations that I implemented while developing Lodash. So Lodash is how many people know what Lodash is? Raise hands. Cool, lots. For those that don't know, it's a utility library. So it's got things to make working with arrays, strings, objects, collections easier. And it covers gaps that exist in the language itself. And in doing so, I originally forked Lodash from an existing library called Underscore. And part of the things that differentiated myself from the competition was performance. Performance, let's see if I get into this next. All right, cool. Some of the things we'll talk about in the presentation is the principles of performance. And so the perf principles, I tried to add a bunch of words that started with the same letter because it looked cool. But it's optimized for correctness. And what that means is that JavaScript developers and the ones that I see a lot will focus on performance to the point that it's a negative. You shouldn't put performance as your highest priority. In this case, I put correctness, functional correctness over performance. Like if you get to the result fast, but you get the wrong result, that's not a good thing, right? So you should always look at balancing performance with other things. And in the case of Lodash, when I implement something, I make sure it's correct and consistent across all of my supported environments, and then worry about performance, and then optimize it. There's also context, too. So I maintain a site called JSPerf, where you can go and benchmark little snippets of code. And a lot of times devs will benchmark things like single quotes or double equals or triple equals, or code with semicolons and code without semicolons, and that is just, it's bananas, right? Like, you shouldn't focus on such micro performance. So everything has context. Whenever you get a readout on JSPerf, it says things like how many operations per second is a given snippet. And a lot of times it's millions and millions of operations a second. And for most use cases, that's the difference between a million, like 10 million and 11 million isn't going to make a difference for your code, right? So that's why there's context. Make sure you you weigh your perf decisions in the context of the thing that you're executing. Also, something I'll mention a bunch is optimized for the common case, and I'll go through and walk through examples of that. Basically, if you have an API that you're exposing, and a lot of times your API may be able to be overloaded, so it can accept an options argument or it can accept one or two ways to be called. You want to optimize it for the way that it's going to be called the most, and you want to make sure that everything else falls off into the slow path that you don't care about. So I'll go through some examples of that. And then another reason to optimize would be to counteract the cost of something. In my case, I wanted to make Lodash cross-browser consistent, and that meant fixing bugs in older environments. And fixing bugs comes with a cost, right? You have more checks, you have more detections, you have to do things like iterate over properties that were missed, and so that's extra overhead to a method call. And so to counteract that cost, I optimized those methods and made them faster, to the point to where you could have code that executed consistently and was faster, which is usually something that doesn't go together, right? You're doing more things and it's faster. And so that's what I did. I used perf to offset the cost of those bug fixes and of added features too. So for example, Lodash has methods that are faster than native alternatives, right? So like r_.map is faster than array prototype map, but it's also doing a lot more too. So it accepts, instead of just a function, you can pass it a string or you can pass it an object, and it will create a predicate function for you. And it does a lot of other things under the hood, and we're still able to do that and be faster. And so it's about counteracting costs, and it's about optimizing for the common case. So I'll be talking about a few of the things that I learned when over the past 2 years. I gave a perf talk right before I created Lodash, and I said some things. And now I have a different opinion on some of those things. So I'll go into what I used to think and now what I think on some of the perf techniques. So you can follow along. I'll be digging into a lot of code, and that's gross. I'm sorry, but there's no way to explain it really. I gotta point to the code and say this is the chunk that's doing this and that. So you can go to github.com/lodash. I'll probably be in the root lodash.js file for most things. So just if I reference a function name or you see a little snippet here, that's me referencing that file. Okay. So the first thing is to optimize for the common case. And I decided to pick an example that really showed this common case. It just so happens it's a wall of text. So we'll see how well I can do this. So here's the common case. Wow, right? Let me zoom in to that just a little bit. Right. Okay. And you don't need to see all the function because I'll talk you through it. But we have a function called matches, and matches creates a function that will evaluate any passed-in object and see if it matches the original object that you passed. So you can do that to filter through an array of objects, right? And the common case for this method is to always evaluate or compare a source object that has one property and it's a primitive value. And with Lodash, we also do something called deep object comparison, where we'll take that value and we'll crawl it and compare arrays, partially compare arrays, and compare nested objects. And that's horribly slow. Like, that's gross. That's gross slow. And that's not the common case. And so if devs were using this method, they would get hit with like just 300% performance degradation on this method for something they never use, right? And that's gross. So what I do is, in this method, I look at if the length of the properties that are passed in is 1, I then say, hey, can I compare this simply, like is strict comparable, which means, can I just go triple equals on this value and do a quick comparison? And if so, then I create this really tiny comparison function, right? So that means for the common case, you're getting this tiny function that doesn't do deep crawling, that allows me to be on par with the competition's implementation. And the competition doesn't support deep crawling of object comparison. So I've got a feature added, and I've got performance, and I'm in the ballpark of them. I've taken uh-ohs. Let's see. Here we go. I've taken it a step further. I just need to remember not to scroll with 2 fingers. So taking it a step further, and normally, let's see if I can get down to it. We'll just do that much for now. We'll keep going. Okay, so here. In the more expensive check, I have a case where I'll be doing a deep object comparison, and that requires me to do a has-own property check, relatively cheap, right, compared to doing is equal, which is here, this has-own property check, and this is equal operation here. But if any point in the time in this comparison, one of the objects fails, so is false, it doesn't match, then I need to exit out of the operation. So normally, I would be doing has-own property check is equal for every element in the collection, right? Has-own property check is equal. Has-own property check is equal. And then if the 90th property of this object failed, it would just return false. So that's a lot of work to just have a fail case, right? And it turns out that when you're filtering objects, a lot of the time is going to be a fail case. It's not going to match the needle in that haystack, right? So what you do is instead is break out those 2 checks, the cheap check and the expensive check, into 2 separate loops. So the first trick is to always do the cheap check first. So before I was doing something like is equal and then the has-own property check. Wrong. you need to do the cheap check, so do the has-own property check first. But what you can do is iterate over all the elements and do a has-own property check, the cheap check first. If at any point it fails, you haven't wasted a lot of effort on JavaScript execution. It'll exit fast without having to ever touch the heavy path. Then only after all the elements pass the light check, then you go back through and do another pass with the heavy check. And that is crazy cool. There's some stuff in here where I'm juggling based on if it is a, let's see, if it is a strict comparison or deep comparison, ignore that. The gist is that it's order your execution of operations from cheap to most expensive, and then if you can, if it makes sense, break them out into 2 separate loops and do all your cheap first, and then do all your more expensive next. Let's see. And that would be optimizing for the common case there. So we were able to get all of that functionality in there and still be performant. Now, it's grosser because it's larger, but that little function can then be fast for every other use. And so I usually say if I can isolate the grossness to just a little bit, I'm OK. In this case, it's not as gross as it could have been. The next thing is abstraction. And I'll have principles of common case throughout all the methods that I'm using. So that was just like a nice case that illustrated it. When I first talked about JavaScript performance a couple years ago, I would always say the easiest way to improve your JavaScript performance is to reduce abstraction, right? If you're doing a function call that calls another function that calls another function that calls another function, that's abstraction, and it'll slow you down, right? That's not the case. You can abstract in a way that you can leverage the optimizations in the JIT, of the engine's JIT, to improve your performance. And so now I'll walk you through how that's done. So now in the current stable version of Lodash, there is code that looks like this, and I'm sorry. This is a function template. This is a template that you would normally use to create HTML. I'm using it to compile a function. And I'll zoom in just because I want gasps. This is gross, right? Like, you can't read this. You look at this and you go, what is this? Now, this is actually I believe, the compiled form of that function, but before that was all strings. No one really wants this in their code. It was the biggest complaint I got from devs looking at Lodash, is that they couldn't understand what was going on there, and it was hurting contributions to the code base because it was something that was too bizarre. Turns out you don't need it. Throw it away. So in the next release, we're going to just leverage abstraction and leverage the JIT in the engine to optimize it for us. And so here's a case. Here's a simple, I believe this is big enough. I probably don't have to zoom. This is a simple, like, for each implementation. Pretty basic. It says, hey, if you've got an array, go and do a for loop over the array, else do this other function that handles consistency over an object, right? Or over a string, or whatever happens to be passed to it. And this is starting off. This is kind of like reducing abstraction, because I'm not calling another function for arrays. I'm not calling a separate function for objects. I'm doing it nested inside the function of for each. But it can be improved. One of the things that I'll do here is that if you look at this snippet of code, what's and say something that's iterating over a collection, what's the thing that's costing you the biggest perf here? And it's this call here. If we go back to the common case, if you're using for each, a lot of the times you're not executing the this arg, right? You're not passing it that third argument for your this binding. Most people don't. Right? You don't need to always do .call if you're never doing a this binding. So the next step is to hoist it out. All right? So we create a small function called base callback that will sit there and do the this binding only if the this value is not undefined. And it will also handle things like the case of method shortcuts. So I can pass a string and it'll handle converting that to a function. I can pass it an object and it'll do that too. But what it does is it leaves the common case, the case of the no this arg, fast, because now it's not doing .call. It allows for engines to type specialize better for that invocation, and you get faster than native performance just by doing that. That's the key. Like if you didn't do that, you'd be slower than the native method. That little one-line change is the secret to that function. And to most of the things that are faster than native if it's dealing with array iteration. So that's the next step, is to just abstract that away. Now, you may have noticed, because of that, I now have a simplified object branch down there at the bottom, too. But that can be taken a step further. So that gives us good performance, but we can get better at that. So here's the next step. And this is to say, hey, if I'm an array, go to a method that's basically taking that for loop and moving it into its own array, or into its own function that handles it. So now this is, hey, if this is array, go the array route, and if it's not, go the base each route. Now this is almost there. We can take it a step further and go here. Now, what this is doing is saying, if you're not passing something that needs to be calling the helper function, don't do it. Just go straight to the array case, because that happens to be the most common case. So now I'm avoiding even the callback sugar if it's the common case, which is to basically have no this binding, it be a function, and it be an array. So I've optimized it there too. There's an alternate syntax that I have on the next slide that's basically it's similar. But what this allows you to do is that now whenever your function becomes hot, especially if you're passing it the same kind of value, so let's say it's the array, the engine will create an alternate form of that function that's specialized for array, and it may inline the array each, right, into the actual function. So it's doing what we were doing before with the code being inlined. So you're getting that performance benefit. But it's not having to deal with the baggage of the object branch being in there too. And so what that allows later is that specialized function can then be qualified to be inlined itself into another function call. So it allows you to inline the inlined code. Again, so it allows the engine to do what it does best, right? Well, it handles the legwork for the optimization for you. So by abstracting and creating specialized functions for just the array or just the object or just your fast path, you're able to get performance optimizations. Now let's see here. All right, so I took out the alternate implementation and replaced it with this one here, which is to talk about a technique I've done with abstraction, which is if you have an exposed API, that has to do it has to accept a lot more things, like what happens if you pass an NaN value? What happens if you pass a string? Do I do error checking on this input that's passed in? If I have to do something like take the arguments object and create a slice of it and turn that into an array. All of that heavy lifting can be done in the external function or the exposed function, right? And then you pass it off to base functions that are specialized to not have to do any of those checks. And so that means that other code in there, I gotta be careful about walking away from this mic, but other code can call that base flatten there instead of having to call the actual exposed flatten. Because the exposed flatten right now accepts a function, accepts the deep flags and all this other stuff, and you can specify, like it automatically will filter out non-array values and arguments objects, and it has all this overhead that you don't need to do internally, right? So you have this base version of the function that's specialized and doesn't do any of the heavy lifting. Something else that you can do here is when you're doing things, there's operations that you can do that affect the engine's ability to optimize a function, that disqualify the function from optimizations. You may see a lot of posts that say, hey, here's performance killers in V8. When I develop Lodash, I look for things that are applied across the board, across engines, so in Firefox, in IE, in V8. There's a common thread of things that you don't do if you want your function to be optimized. And so one of them is converting your arguments object to an array. If you do array prototype.slice your arguments object, you've disqualified that function from optimizations there because the engine punts on that. It goes, you're touching the arguments object, gross. No optimizations for you. But what's okay is if you have that exposed function that's doing that arguments object conversion, if it's just that tiny external function and it's passing off to another function that can get optimized because it's not doing any of that work. So I create a new function to do things like try catch. A try catch will disqualify your function from optimizations, right? Some are more fine-grained into where the deop happens, but as a general rule, since you're developing for more than one browser, you would want to abstract that try catch into its own function. That way, that function that has the try catch is deoptimized, but all it's doing is the try catch block in there with your code. And so in the next version of Lodash, we'll have a function called _.attempt. Which allows you to execute code, and it will if it errors, it will return the error object, and if not, it will return the return value. So that way, if you're developing your own code, you don't have to worry about that perf trap. Just use the API, and you'll get the benefit of not de-optimizing your function. So that's a nifty thing to do, is to, if you have an exposed API, have it do the heavy lifting, and anything that's going to disqualify it, and then pass it off to a specialized function that doesn't even care about it. So like my specialized functions, it doesn't care. It doesn't do any checks to validate that the number is actually a number. I know by the time it gets there, it's a number. It doesn't do any checks to see if the value is truthy, like the collection is truthy. I do all of those checks ahead of time in the other functions. So they get optimized, they get inlined better. There's no disqualifications of performance for them. And so that's where abstraction is really, really good. And you don't get that whenever you inline and try to do all that stuff yourself, right? Then all of a sudden, the engine looks at that and goes, I can't inline this. It's past my limit. So V8 has a limit based on the actual number, the actual character size of the body, the function body, i.e. Chakra is based on bytecode generated. I'm not sure what Firefox does, but it's basically small functions get inlined better than large functions. And if you branch off for specialized paths, like the previous example with the array branch and the object branch, then that even the inline form of that could potentially be inlined as well. So that's cool. So that is abstraction. All right. The next one is bye-bye built-ins. And I found this. It took me a while to find this gist, but I like it. So it really fits with what I'm about to say. So before I developed Lodash, I looked at native methods, and the performance was pretty crappy. And it turns out they haven't really been optimized over the years. And it can affect, depending on the implementation in the engine, like if your function gets inlined or not based on if it can cross boundaries of if the JavaScript version, if your built-in is implemented in JavaScript, maybe it can be inlined better. But regardless, they're always doing extra work that you're normally not doing. So they're not optimized for the common case, right? You're usually working with a dense array. You're usually not caring about the this binding. You can do this a lot faster on your own. So in certain cases where I've profiled the implementations across multiple browsers and found that JavaScript versions were faster, I've used them. Now, that's bonus. The real reason was I wanted a way to iterate over arrays consistently, and I couldn't do that with native methods or shims because older versions of IE would treat sparse arrays differently than modern versions. You could have an array with an undefined value, like a literal undefined value, and older IE, so IE less than 9, would treat it as a whole in the array, which would cause iterating over arrays to be wonky. And if you use a shim, you're going to get that bug. There's no way around it unless you treat all arrays as dense. And so that's where I was coming from. And then I looked at it and was like, holy crap, that's really fast. So awesome. So I started at it with consistency, and then the bonus was performance. And this isn't like a ditch all your built-ins. This is profile, figure out what's right, and where you can squeeze the performance and add functionality. So for example, I'm able to add all this functionality to a method and still be faster than native, which is great. Devs don't notice the difference. They get more functionality. They may get a speed boost. That's bonus. It's great. There's also cases where you don't want to say bye-bye to built-ins. There's some that are really, really cool, and I'll be talking about some ES6 functionality that's available in all modern browsers right now that you can use that gives you crazy performance. And in this case, there's also some ES5 stuff too. Let's see if I get into that before I go too far. All right, so here's a filter implementation. Again, a basic implementation of filter. This happens to be crazy fast. Now, what I'm not doing here is doing any, if you notice, there's no this binding. That's because this is that base method. Remember, I created those tiny methods that are called out to by the other functions? These are the small functions. These are the optimized functions. All right, so before I get into the ES6, I want to talk about the ES5 goodness. So if you're ever iterating over an object and you're doing for in plus has own property, that's gross, it's slow, don't do it. I would even say shim it. Shim it and then use object.keys. Object.keys is full of when it comes to iterating over objects. You can't get faster in your JavaScript implementation of that. There's no way. Like, it's just where other implementations have dropped the ball, object.keys has picked it up. Like, it's really the best method for that. So we use that internally, Lodash does. So for _.keys, if it's possible, we use native object.keys. Now, when you get into edge case land, there's some bugs across browsers, even modern browsers, when it comes to iterating certain objects, and so we fix some of those bugs too. So I'd say if you're using Lodash, continue to. We probably fix more bugs than a shim would. So that's cool. Also, another one is checking if something is an array. Array.isArray, awesome, fast way to check if something is an array. The shim for that is really slow, but all modern browsers have it, so take advantage of it. And even older browsers now have it because it's been around for a while. So as long as you're not going so far back, like IE8, does that have it? I don't even know anymore because I do a feature test for it, and if it doesn't exist, I have a fallback, and if it does, I use it. I'd say try it out. It's pretty cool. But now off to ES6 and the coolness that is available in all browsers right now. And the thing that I really love in Lodash is getting to leverage set, ES6 set. So when devs switched from underscore to Lodash, the main thing that they say improved performance was large array iteration, searching for a needle in a haystack, basically. So index of, if they're having to do a unique, if they're having to do an intersection, a union, anything that deals with large arrays and looking up a value in them, we perform better. And in the next version, we're leveraging ES6 set instead of using our internal implementation of ES6 set. We're just using the native because it's really cool. And I'll explain why now. So one of the cool things about a set is that it contains unique values inherently. If you try to, in this case, add, but I've aliased it as push because in the internal implementation that Lodash uses, we think it's an array. It looks like an array because it's got the method. I use it, if native set is supported, then I use it in place of the array that's normally returned. That's why I kind of make it look like an array. And that's why if it's found, it returns 0 and -1 because index of is going to return an index or a -1, and my implementation doesn't care. It just says, oh, this looks like it's found, and it's not found. But anyways, set allows you to cram all kinds of objects into it, and it automatically rejects the duplicates. So the set's always going to have unique characters or unique objects. So if you want to find something that's unique, you just push all your elements into the set, and then you just read them back out, right? And then you get your unique array. And it doesn't do all of this array traversing. Like if it's 1,000 elements, you don't have to sit there for every single element and crawl the array, right? That's gross. This way it allows you to do it really, really fast. And also, when you do a set and you're looking to see if an object exists in there, it's not having to do a linear lookup. It's just going, hey, is this in my set? Yes. All right. It's not having to go 0. Is it there? No. 1. Is it there? No. 2. Is it there? So ES6 set is great. What I'm doing here, though, is I've kind of hidden away the feature detect. But I detect if set exists earlier in the code and if it's not shimmed. Because we want to leverage the native goodness, right? So I don't use object.keys if it's been shimmed, because I trust my code better than some third-party code, right? Like, we don't know if they're using some old version of prototype that's paved over ES5 methods with their own because they didn't check to see if they existed yet. So we avoid doing that. We say, let's not use a shimmed method. Let's only use it if it's native. So I do that, and I set the value inside my closure per set. So if it exists, it's truthy, and if not, it's falsy. Normally, you would not want to do that without doing checks and assigning variable references because it would be an undefined variable lookup, and that's gross, and your code will error. But I check that it exists, and if it does, I implement the method. Then later on, I say, hey, if create cache is truthy because it's either going to be false or a function, then I use create cache in my code. And that is ES6 set. And the reason there's probably shorter ways of using ES6 set, right? That you can add values a lot easier in certain engines that support more of the ES6 functionality. But this is the cross section of functionality that works in all modern browsers. When I say all modern browsers, I'm probably excluding Safari. But whatever. They're going to have Safari 8 soon enough, right? So feature test for it, use it when it's available. It's great. So this is a one from last year that I liked enough to bring back because I got outrage in the Twitter feed from this. I don't know if you can see that. I'll scroll in a little bit. Zoom in. So before I said, hey, if you're not using this and this binding, don't bind your functions because it's slow. You can detect that a function has a this reference in it because it's not quite spec'd per se now. ES6 maybe does a little more. But if you two-string a function, it'll kind of generate the function source, right? So you can use a regex to say, hey, does that thing have a this reference? And if it does, then you can know that it needs to leverage the this binding. And if it doesn't, then you can not do it, right? Not do the .call, not do the .apply, do the optimized code path, right? So this was cool back then. There's some problems with it. Turns out that on certain resource-restricted devices, like some mobile phones and certain Windows apps, you can't coerce a function to a string without incurring a cost. In some cases, it's loading bytecode. In some cases, it's memory impact. So I have some feature detections now to kind of avoid this. So I'd say use with caution. That's why it's unorthodox, because it's cool, but yeah. So there's something else I've done here too, which is first check to see if the function can be decompiled. And so, hey, I've got like this big, like, hey, this is the environments that support it. Yay, and here's what I return false for. And I'm testing my one function to see if it can recognize the this reference in it. Now that function is crazy large, so if it can find the this value in there, then it's supported. So I do that. But then there's something else too. A lot of times you're dealing with functions that you can't store metadata on, and so that's something I'll be talking about. Oh, I've got like just a couple of minutes left. Later is metadata, and so I detect if a function can support the name property, because if chances are, normally when you're calling an array function or like a map or a filter, a lot of times that's just a function that's created at the runtime, right? Like you're passing it the function right there. So storing metadata doesn't make any sense because that metadata is just going to be written to and then thrown away. So I detect if the function has a name property, and if it does, I go, okay, it's probably safe to write metadata to. And so that leads me into the next slide. And we're going to ignore that because I talked about it. Metadata. So this. It's all right, folks. I got this. Metadata. When you create a function bind, or you do a partial, or a curry, or a partial write, you're wrapping the original function, right? And if you call partial on a partial or something that's already been bound, you're wrapping an already wrapped function. And so to avoid that, especially because devs like functional programming, right, where you're always currying this or partialing that, and then applying another curry or a partial onto something that's already curried or partialed, the performance impact of that is just bogging down the function because you're having to twist through all these wrappers to get to the original function. But if you store metadata on the actual function, this is what Lodash does, we flatten everything down to a single function, a single wrapper around the function. So no matter how many times you call bind on an already bound function, or bind, curry, partial, partial write, wrap any of those combinations on a function, you can call them 15 times and wrap it 15 levels deep. It's only ever one function call away from the actual original function. And that's because we store metadata on the function that then flattens all of the attributes down. So this is why I leveraged a bit mask for the first time ever in JavaScript for me to implement this. And I thought, wow, that's what they're used for. Instead of having like 8 arguments to pass to this function, I can just store all the configuration inside a bitmask. So that's what I've done. I basically bolt on an array to a function if object.define property exists, because I don't want this metadata to be observed through object iteration. So I make it non-enumerable. So engines that have that get that benefit. If not, the function should execute just like it normally does. The metadata should not make, and this was tricky because before you could leverage that metadata to do a lot of cool stuff, but it can't have any other side effect on there. It should be able to be pulled out and your function still operate. So here is another view of that. And this is me doing things like detecting values, like cloning the partial right arguments and cloning the partial left arguments and merging arguments together. It gets really trippy. And honestly, I have to throw unit tests at this, but it allows that really cool flattening down of functions. And I've noticed that there's certain engines that optimize like native function bind this way too, that will, no matter how many times you bind a function, it's a fixed cost to that function binding. And that's not consistent across engines. So I do that here. I deal with bitmasks. I try to throw a bunch of comments at it. But what's great is that if your engine doesn't support it, it doesn't matter. It pulls it out. Things still work. So that's really cool. And let's see. Things. OK. So I'm about out of time. There's Lodash.com. There's the repo Lodash. If you go to Lodash itself, you'll find all the different builds of Lodash. So there's AMD, there's NPM, there's Node, there's ES6, because in the next release, we will support a fully tested implementation of ES6 classes that you can use, and then use your favorite transpiler and transpile to the module format of your choice. So we do that too. Also, JSPerf. Please use JSPerf responsibly. Don't go down the rabbit hole of micro ops. Like, profile your code first. Like, wait for your code to have a performance issue, and then use JSPerf to test different implementations of the bottlenecked code. Like, that's the way to do it. Profile your code first. Don't go crazy. Like, I get devs that'll say, hey, you could get faster execution of this if you do plus plus versus minus minus. Nah. Just say no to micro ops. Test first. I'm competitive, so I have to look at the library landscape around me and say, all right, their version is this fast. My version needs to be at least that fast or better. And devs will end up building on top of a library. That's why I focus on some performance stuff. But in cases that aren't being built on, like more stuff isn't being built on top of your stuff, just apply context to it. Like, if this code is only going to be executed once, you don't need to micro-op that stuff. Like, who cares? Make it as functional and chainy as you want. It doesn't matter the performance impact. And then also you can follow me on Twitter at jdalton. Cool. That's my talk. Questions? Yes.
How do you check if it's shimmed?
Cool. Yeah. So that's another one of my favorite things, but it's not really perf. But I'll show you anyways. OK. So is native. Here's how I do that. Is native. So that's not going to really help you there either. Let's say this. There is native equals here. Here's the secret sauce. I decompile a native function. I strip out any identifying characteristics of that function. So right now I'm using object.prototype.toString. Right? So I've got a reference of toString somewhere else up there. That's why it just says toString. And I remove the toString word from it. So that means that it should be generic enough to where any other native function where I remove its identifier from it should kind of look like that when I decompile it. And so normally when you decompile a native function, it'll go the function name and it'll say bracket native code bracket, right? That's the normal case. But this, using a regex and decompiling the function will allow me to support different cases, because in certain platforms it's not just native code. Other libraries do this too, like Ember will detect if it's shimmed, and they just use like a native code inference, and most of them do. I saw a pull request on YUI where they did this, and I loved it. Like using the own function source to extract the pattern for a native function was awesome. So I did that. I added a little extra check too in there for what Rhino prints out. Rhino in Java runtimes will add some extra like for this or that into it too, so I stripped that out. But that allows me to check, because most shims don't shim the two-string representation of the function, right? And even if they did, later on, down there where I'm actually using it, I'm using function.prototype.toString.call, and that allows me to bypass any custom two-string they have on that function, so I can get straight to the actual two-string value. So no matter if they've tried to trick me, I can still detect the custom or the native method. So yeah, there's that. I don't know if I repeated the question. That whole thing was about how do you detect a shim? Cool. Any other questions? I saw more hands that were up the first time. Yes?
Can you talk about taking like a try-catch and
So that's it. Okay. Different parts of the try-catch can be optimized by engines. Different engines do different things with that, right? So like some of them, if you're not doing the catch, but you have a finally, it may be able to optimize it. But I'm programming for performance across the board, and so across the board, that hasn't been optimized away yet. So that's why you do it. There are probably some limitations to it. Like I don't know if they could optimize the entire thing away. I know that I've seen resistance to trying to solve that problem. So I would say that if ES5 methods aren't optimized, try-catch is a lot lower on their list of things to optimize. So the lovely thing about browser competition is that if one browser finds a way, it puts pressure on the other browser implementations because we're very competitive. So I would say that's probably a good way into getting something optimized, is to get one of them to do the legwork and optimize it, and that'll put pressure on the other vendors. That's also a good thing to try to get whatever you want optimized included into a benchmark, because browser vendors love benchmarks. So I would say that's another case too. Like, hey, try to do a pull request against Octane or Kraken or SunSpider or whatever benchmark. Like WebKit's got 2 new benchmarks, right? Do that there, and then browser vendors will pay attention to it. So, cool. Any other questions? Oh, yes? Right, and so by abstracting that into a function itself, though, you avoid that issue for other engines too. So that's why I instead of recommending like all devs do that, I made it into like an easy utility function, right? So then they can just say attempt, and it becomes just part of their normal sugar that they use with a library. And that way they don't have to think about it like, hey, is the engine optimized this yet or not? If they use the utility method, they'll get the optimization either way. So, cool. Any other questions? Someone scratching their head is not a question. Okay, cool, thank you. Awesome.